Welcome back. This is lecture 22. Sorry, it's probably lecture 23. We started discussing about the effects of distortion, or rather how to quantify distortion in a nonlinear system, and we also briefly saw about how to go about reducing distortion, given that your transistor is biased in saturation, and we are mostly concerned about the GM distortion, that is the VGS to IDS distortion, right? And we saw that again, like before, it makes sense to bias your transistor with as high a voltage overdrive as one can, right? So before going into the distortion piece, it occurred to me that while we did the noise analysis, where we also came up with the conclusion that we really need to bias, we want to bias each transistor with the maximum possible overdrive in order to maximize omega t and hence improve our noise figure, right? So that also had the same outcome, that is, increasing overdrive improves noise figure, just like increasing overdrive improves distortion, right? So the part that I forgot to mention while doing the noise analysis of cascode was the fact that what is the intuition behind as your frequency increases, the noise contribution of the cascode also increases, right? So the intuition is as follows. So let's assume that this is grounded. I mean, that's what anyway we assume. And there is a capacitor to ground, and this is our noise current source, and this is the current loop, right? That we are interested in, right? So what happens as the frequency increases? So let's say at infinite frequency, what happens? At infinite frequency, this capacitor is shorted, so the entirety of the noise flows through the output short circuit, comes back and goes into the current source. The entire GM is bypassed, right? At infinite frequency, your transistor gets bypassed, right? So this noise current source, at least in the model that we have, even though I understand that the noise current is a part of the transistor, but in this case we have taken the noise current source out and assume the transistor is ideal. So in this model, the transistor is essentially bypassed and the noise circulates in the output short, right? And hence, because the noise goes to the output, the entire noise comes out. What happens at so let me also draw it out. So this is at omega tends to infinity, right? So all your noise current flows through the loop, flows through the output loop, hence you capture the noise current at the output. What happens at DC? If I follow the same picture, what happens at DC? Or at very low frequency? So this is open circuited, your capacitor is open circuited. So no current at the output, right? So this noise current circulates through the transistor, right? So this is at omega tends to 0, correct? So obviously, as you can see that as you keep on increasing frequency, the capacitor, this capacitor starts coming into picture, and it gives a path for the noise, the cascode noise, to come out. Now at omega t, right? Omega t is kind of, or the GM over CGS is that cutoff frequency where the impedance of the impedance offered at the source by the transistor is equal to the impedance offered by the capacitor, right? So at omega t, or rather at any frequency, what is the impedance looking this side? This is 1 over Gm. What is the impedance looking this side? This is 1 over j omega Cp. At omega t, that is when 1 over Gm becomes equal to 1 over omega Cp, that is omega is equal to Gm over Cp, which is omega t, which in this context is omega t, but you understand it's some Gm over some C associated with that node. The current kind of magnitude of the currents is equal, and that kind of gives you a cutoff frequency as to where most of the noise current from the cascode comes out. So you would like to bias your transistor in such a way that you are sufficiently away on the lower side of Gm over Cp, and that is why you need to bias your transistor with minimum capacitance while having maximum Gm, which is only possible if you have lot of overdrive, right? So that is the intuition behind as to why you would like to have the the noise as to bias the cascode with high overdrive. Now the practical problem with biasing the cascode with high overdrive is that you will end up with headroom issues. So that is why in most design considerations you do not actually give the cascode lot of overdrive, but you kind of simulate and check, right, for what particular overdrive, or how far below your omega t you need to be, because if you are already 100x below, you don't have a problem. You can probably be okay with even being 20x below, so below omega t. So that's why the design trade-off comes in. So you do that rough analysis, and then you simulate and verify as to do I really need to give that amount of headroom to be so far away from omega t, or maybe 1 decade away from omega t, or maybe 20x away from omega t is good enough, right? So that's the design call one has to make after 1 or 2 iterations of the design, right? Okay, so let's proceed with our discussion on distortion. So having cleared that the intuition about noise from the cascode up, let's continue our discussion on distortion and how to measure it, and what are the distortion parameters that we typically encounter in any RF system, right? So from the example that we did in the last lecture, you should readily appreciate the fact that if you have a second order nonlinearity, when I say a second order nonlinearity, I essentially mean, let's say I have a system whose input output characteristics is modeled as, if input is Vi, this is some f of Vi, and where f for V naught is f of Vi, which is, let's say, modeled as some constant Vc plus some linear term A1 Vi plus A2 Vi squared, right? So A1, A2 and Vc are where A1 is essentially, you can think of these terms A1, A2, and if I call this one A0 just for consistency, you can assume that these are proportional to the coefficients of the Taylor series expansion of any nonlinear function, right? Continuously differentiable nonlinear function f of Vi. So the A1, A2, they are, by the way, they are not exactly the same as Taylor series coefficients. What I mean is they are not exactly the same as what you will get by differentiating f of Vi, but as we understand that if I expand f of vi into Taylor series, I am going to get terms which are, there will be a constant term, there will be a term which is proportional to vi, there will be a term proportional to vi squared, then vi cube, and so on till infinity. If I limit this expansion to vi squared, then we are basically saying that we are assuming a system which has only second order nonlinearity. I mean, a case in point is a transistor which has, which is modeled as a square law, right? Having said that, we understand that no transistor is a square law model that has a square law. Real transistor is a square law model. The models are highly complicated, and you can have all orders of harmonics or all orders of Taylor series, right? But for the sake of this discussion at present, we are limiting ourselves to second order. And further, we saw that if Vi is EP cosine omega naught t, right, and we pass this system through a second order nonlinear system, the output has three components. It has a DC term, which is not particularly surprising because you kind of always end up with some biases. You have omega naught term, right, which is also not surprising because this is a kind of, if I am trying to make a LTI system, I expect the output to also have a omega naught term, but because of the nonlinearity, because of the squared term, I am ending up getting something at 2 omega naught. So this is something that we saw in the earlier lecture, and one might then say that, hey, I understand our RF systems are narrowband, right? So around 1 gigahertz, maybe you have a couple of megahertz or 10 megahertz of bandwidth. If omega naught or f naught is at 1 gigahertz, then 2 omega naught is at 2 gigahertz, then they can be filtered out, right? I just put a nice bandpass filter that I do not have to bother about 2 omega naught at all, right? So in this example that I gave you just now, it is true that you do not have to bother at all, but the problem is you never actually send a single tone, right? Because, and in general, you will be sending multiple tones. In fact, might not be even sending tones, you will probably be sending aperiodic signals or some signal which has some random information, right? So a more accurate way of representing distortion in RF system, that's why, is to model a system in which multiple tones are being sent simultaneously. A simpler version of it for analysis purposes is you send two tones which are close to each other. That is a more realistic way of modeling, right? So in pictorial view, so what we are essentially saying is that, let's say I have a center frequency of f naught, and this is my band, right? So instead of sending f naught, I will send two tones which are at, let's say, close to f naught, and I call this f1, and I send f2, or omega 1 and omega 2, right? So what happens if I send these two tones? Now note that in the context of a radio receiver that we have been talking about, you should understand that if you have an LNA, this will be followed by a mixer, right? And if I call, and the mixer will be operating at FLO, and the input will probably be at f1 and f2, where maybe f1 is FLO plus delta f1 and f2 is FLO plus delta f2, right? So, and we are interested in, after the mixer, there is probably an ideal low pass filter, right? We are interested in observing the final output here. So we are essentially trying to figure out what is the distortion component that comes here, right? Because after this, what I'm going to have some baseband circuitry. Maybe I'll have an ADC or sampler or something that will come after the low pass filter. I'm trying to find out, after all this chain has happened, what is the distortion what is the effect of this distortion at this point. Now in this context, you see that if you send in a monotone signal at, let's say, FLO, right, the distortion component due to second order distortion will be a second harmonic of FLO, that is twice FLO, and that will be way out of band. So this, let's say I call this FBP, right, which is much less than FLO, right. So the twice FLO, if I have twice FLO here, the twice FLO will mix with FLO and create another FLO and 3 FLO, and both of them will be outside the band of the low pass filter, and at the output of the low pass filter I won't get anything, so I'll be good, right. So but that is not a realistic scenario. As I pointed out, we generally tend to send multiple tones at a time. So we would like to see what happens if we send 2 tones, right. So let's do that experiment and see, or rather in this case let's do the analysis. So if I send 2 tones, so I have VP, so your VI is VP. Let's, for the time being, assume that both the tones are of equal strength, right. So what do we get at V0? V0, we get the constant A0, then we get the linear term, which is not of surprise, that we are anyway supposed to get, but we get an additional term which is the square of this guy, right? P whole square, right? So these two I understand, so I will not spend time on them. Let's focus on this guy, right? So if I expand that, what do I get? I get, if I focus on that guy, so what do I get? So I get A2 times, get Vp squared cosine squared omega 1t plus Vp squared cosine squared omega 2t plus twice Vp squared cosine omega 1t cosine omega 2. And further, we understand that this will be broken down into one DC term and one term at 2 omega 1. This will again break down into one DC term and one term at 2 omega 2. But this term is going to break up into 2 non-DC terms. So one of them will be, if I expand this, I will get Vp squared A2 Vp squared cosine omega 1 minus omega 2t and plus A2 Vp squared cosine omega 1 plus omega 2t, right? Okay. So can you comment on the approximate frequency of omega 1 and omega 2, omega 1 plus omega 2, when omega 1 is equal to omega LO plus delta omega 1 and omega 2 equal to omega LO plus delta omega 2, and with the understanding that delta omega 1 and omega 2 are much less than omega LO. If that is the case, then we understand that omega 1 plus omega 2 is approximately equal to 2 omega LO. Correct? So now in the context of your LNA being driven by a mixer having omega LO as the clock, and then in the context of we are having a low pass filter whose cutoff frequency is much less than omega LO, do you think this input at 2 omega LO is of significance? Clearly no, because this is going to create a tone. This is going to create a tone at omega LO, 3 omega LO, and if you and so on, right? So if I assume this is a sinusoidal LO, right? Okay. So which means that whatever the low pass filter I have, that is going to filter out this component. We'll come back to this discussion in couple of minutes if uh, this is not a sinusoidal clock, right? Which is actually a real thing. But now let's focus our attention to the other term, the omega 1 minus omega 2. So what happens with that term? Note that this is not DC, correct? If it were a DC, then I could have put a capacitor as a DC blocking capacitor and got rid of it. But this is omega 1 minus omega 2, right? Which is sufficiently low frequency, because omega and omega 2 are, this is equal to essentially delta omega 1 minus delta omega 2, which is closer to DC. Okay. Now note that if your clock, right? If your clock is a square wave clock, right? It has a strong DC component to it. Correct? It has a strong DC component to it. DC component present. Which means your LO also has a 0, right? You had a 0 here also, but it was of not much of use, because even if 2 omega LO passes, that because of 0, it's not a problem. But in this case, it's a problem because your delta omega minus delta omega 2 is going to get multiplied with 0, and basically it is going to pass on, and you are going to get delta omega 1 minus delta omega 2 here also. Correct? You are going to get the higher term also by multiplying with omega LO, but we are not considering that, because ultimately the low pass filter will filter that term out. But you are going to get delta omega 1 minus delta omega 2 here also, right? Okay. So what's the issue? So as you can see that you did not have a signal at delta omega 1 minus delta omega 2. In fact, you had signals here. The original signals were at omega LO plus delta omega 1 and omega LO plus delta omega 2. So which essentially means that here we were supposed to get delta omega 1 and delta omega 2, right? And other terms, right? And other terms. But at the output, ideally you would want delta omega 1 and delta omega 2. But instead you are getting delta omega 1, delta omega 2 term and the additional term of delta omega 1 minus delta omega 2, right? So that additional term that you are getting, what is the strength of that term? So by the way, what is the strength of this term of delta omega 1 and delta omega 2? What is the amplitude of those terms? The main amplitude of this term is Vp times A1, right? This is Vp times A1, right? So these terms have an amplitude of Vp times A1 and Vp times A1. But what is the amplitude of this term? This term is arising out of this guy. So essentially, its strength is A2 times Vp squared, right? So its strength is Vp squared times A2, right? And as we have talked about in the previous lecture, this unwanted term, this bad term so-called, that rises faster than the strength of the term increases faster than the desired term, right? It goes by Vp squared, the other one goes at Vp, right? So In order to characterize your system, you have to understand whether your system has good distortion performance or poor distortion performance. Ideally, what you want to do, you have to ensure that Vp squared times A2 is much lesser than Vp times A1. By the way, there is a technical name to this. This term that has arisen out of cross multiplication of two input signals because of the effect of nonlinearity, second order nonlinearity. It is called the intermodulation component. An intermodulation component due to the second harmonic, hence it's called IM2, right? So this omega 1 minus omega 2 is referred to as, or rather I should say, the component that is called intermodulation component 2 or IM2, right? When measured at output, this is called OIM2, and when referred back to the input, this is called IIM2, right? So when I say referred back, what I mean, you basically at the input you really don't have distortion, right? Input is a pure sinusoid, but just like noise, you would like to refer everything back to the input to understand what is the amount of signal, what is the amount of effective signal that you can have before you cause certain amount of distortion at the output. So IIM2 is typically measured as OIM2 divided by the linear gain, right? And if you are in dBs, you basically subtract the gain, right? So that's how we measure it. But now what is the measure of? There is a technical way of expressing what is the strength of the second order distortion, or how bad or good your system is with regards to IM2, and that is essentially measured as follows. So let's say you plot your fundamental and these IM2 components with P in, right? P in dBm, and you plot P out also in dBm, and what is the strength of the fundamental component that you are going to see? The fundamental component is A1 times Vp. If I am only considering one of the signals, right? It's both of them are essentially having the same transfer function approximately. I can as well consider one of them. So it's A1 times Vp. So let's just say A1 times Vp, which means that in terms of dB terms, for every 1 dB increase in Vp, the output will also increase by 1 dB, right? So essentially this is a linear line, right, of 1 dB per decade slope, right? So this is 1 dB, not decade, 1 dB per dB slope. So for every 1 dB increase in the input, the output goes by 1 dB, right? So this is the strength of the fundamental component, right? So this is the plot of the fundamental. Similarly, if I plot the strength of OIM2, right? So what will happen, for every dB increase in the input, your output will go by 2 dB because it will be squared, right? So essentially that guy will go by. Obviously, at sufficiently low frequencies, you are expecting the distortion to be much smaller than the fundamental. So I would expect it to be much smaller. But the key thing is that it is going to increase by 2 dB per dB. So it is going to increase by 2 dB per dB. Okay. So now, if you keep increasing these amplitudes, right? And if you keep increasing this amplitude, these two plots are eventually going to meet. And the point where these two plots the extrapolated plots actually meet is called a second order intercept, right? For IM2. So, and it is called out OIP2 if you are referring it to, if you are considering the output power. For the input, it's called IIP2, right? So essentially, these are the intercept points at which the extrapolated fundamental and the extrapolated IM2 plots essentially meet, right? So why I'm saying extrapolated? I'm saying this it is extrapolated because when you do these simulations with actual circuits, they will not be limited to a second order distortion, right? They will have all sorts of other distortion which will tend to dominate as you keep increasing the strength of the input. And when that happens, you will not get this nice straight lines. You can immediately understand that if you look at the strength of the second of the fundamental itself, right? You see that your fundamental is going to get affected by A2 also, because the expansion of this Vp squared cosine square omega 1 is also going to affect A2, right? And so, which essentially means that your A2 should not be ideally a 1 dB per dB line, right? It should get affected by that A2 also, right? So that is why these initial, when you do an experiment or even when you do simulation, you start off with extremely low values of the input signal. Now, what is extremely low is again subjective, because ultimately it depends on how much distortion you have, right? So the typical way of running the simulation is you choose any point to start off and then see what is the slope of the fundamental and what is the slope of the IM2 line. If the fundamental is not 1 dB per dB, which means that you have or the IM2 line is not 2 dB per dB, which means that you have higher than you have chosen higher power, for which you can only extract IM2. Other harmonics, other higher order terms are probably affecting your simulation. So you have to reduce your power, right? Start off with low power, minus 40 dBm, minus 50 dBm of input power, and then check what you get. If that is also not sufficient, you reduce further and you keep checking, right? So once you do this, you are going to, the simulator in some simulators will probably throw out a plot like this. In some simulators you will not get the plot like this. You have to export in Excel or you have to export in some software and plot and check where these two plots meet. But the important thing is that the point where these two plots meet has a technical term, and that term is OIP2, right? Or IIP2 if I refer it back to the input. And if I have to do it mathematically, that essentially means that A1, so basically at OIP2, A1 times Vp should be equal to A2 times Vp squared, right? So why A2 times Vp squared? Because strength of this bad term is Vp squared times A2. So, which essentially means that Vp is equal to A1 by A2, right? So this in plain English means that for an input amplitude of Vp is equal to A1 by A2, the strength of IM2 is equal to the strength of fundamental, right? So this when referred to the output, we call this so obviously Vp is the input amplitude, so hence this is is the IIP2 is equal to, right? So when you express this in dBm, so that sometimes you are going to see some papers or some data sheets refer to IIP2 in terms of dBm. That's what they essentially mean. Okay. So now let me go back to the part that I did not address immediately. That what happens if I undertake, if I assume that this has 2 omega LO component also, which it can have if it's not a 50% duty cycle, right? Assume this is an illustrative example. So let's assume it has a 2 omega LO component. So which means that which means omega 1 plus omega 2, which I approximated as 2 omega LO, will also have 2 omega LO. It is, if I don't do the approximation, this will be 2 omega LO plus delta omega 1 plus delta omega 2, right? Correct? So if the 2 omega LO component mixes with this, I am going to have delta omega 1 plus delta omega 2, which means that the output also I am going to have delta omega 1 and delta omega 2. So what will be the strength of this component? Again, if I assume, again, the part that I implicitly assumed is that the low pass filter has a perfect pass band of amplitude of h of 1, right? So even if I assume that, what will be the strength of this delta omega 1 plus delta omega 2? It will be again be Vp squared times A2 times the strength of this sideband of the LO, right? So having said that, that will still be Vp squared times A2 times some factor, but the factor will generally be smaller than 1, right? So that is why your IIP2 is often characterized with not with respect to this this component, but with respect to the other component, that is omega 1 minus omega 2, and which mixes with the fundamental of the with the strength of omega 1 minus omega 2, which mixes with the DC part of the input, right? DC part of the clock. Now, as you might have figured out by now, if the clock does not have a DC, then it seems like, or rather, if the clock does not have a DC or 2 omega LO or 4 omega LO and all those things, right? Then it seems like we will not have a problem of IIP2 at all. And indeed, right? So if you have a differential clock, right? So in many cases, you will probably not face this problem of IIP2. Similarly, in general, if you have a differential signal, I'm making that point is, so let's say this is Vi, and I know that the output is A0 plus A1 Vi plus A2 Vi squared. So I take another copy of this function. You can assume that I copied the same LNA twice, right? And I applied the same input to both of them. Sorry, I made a mistake. So I apply a positive Vi to that first top block, and I apply negative Vi to the bottom block. So that bottom block output will be A0 minus A1 Vi plus A2 Vi squared. And now if I take a difference of these outputs, right? So if I take a difference of these outputs, what will I get? I will get only 2A1 Vi, right? There is neither a DC term nor a second order distortion, right? So this is generally, by the way, this type of taking an identical copy and applying a differential input or antisymmetric input to the input and then subtracting them, this is often called pseudo differential or fully differential implementation of any network. And as it turns out, I mean, you can easily extend it to any amount of any type of polynomial, and you can see that if you do this, all the even order terms will get cancelled, and you will be only left with odd order terms, right? You will be left with A1. If I say that it has A3 also, which I have not really talked about, but it's not very difficult to extrapolate. right? So this will be minus A3 VI cube. So you are going to have another term plus 2A3 VI cube, and so on, right? So all the fully differential implementation, or in this case, just a differential implementation. So differential implementation kills even order terms, right? So which means that it kind of kills your even order harmonics also, right? So you will not have 2 omega and all those terms, which means that the entire IIP2 will essentially become irrelevant, right? The IIP2 won't even exist. So no second order terms means IIP2 in principle is infinite, right? Okay, okay, fine. But now, as you can see that the third order term will not get cancelled, so they will remain. So which means that we need a metric to characterize, or rather, we need a metric to understand how to characterize the third order effect of the third order distortion, right? So, and we'll do the same thing like before, right? So so let's say we limit ourselves to only third order terms, right? And we'll assume that the no second order of the DC term exists. So let's say your f of whatever your function, if this is vi, is a1 vi plus a3 vi cube, right? It might have second order terms, but I'm not including them, because ultimately if I do a differential, it will go off, right? And now again, like before, let's assume your vi is, by the way, one question before I move forward, I probably needed to address this. So what is the unit of a1 over a2? Note that what is your v naught was a1 vi plus a2 vi squared plus a naught, right? So clearly, the unit of a1 is the voltage inverse, and unit of a2 is voltage minus 2. That is why a1 over a2 has the unit of voltage, right? So that is something you have to keep in mind. Okay, fine. Similarly, what will be the unit of a3? It will be v to the power minus 3. Okay, okay, fine. So if I input is Vp cosine omega 1t plus Vp cosine omega 2t, again the assumption is omega 1 is equal to omega LO plus delta omega 1, and omega 2 is omega LO plus delta omega 2, where delta omega 1 and 2 is much less than omega LO, right? Again, generally we will take this assumption. Then let's concentrate on this term only. I do not want to carry forward that a1 vi term, because I know that's a linear term that we are anyway going to have, right? So if I expand the cubic nonlinearity, what will I get? Vp cosine omega 1t plus Vp cosine omega 2t. Here I have a3 times whole cube. So I am going to get this usual cubic terms, Vp cube cosine cube omega 1t plus Vp cube cosine cube omega 2t, plus I am going to get two interesting terms, that is 3 Vp cube cosine square omega 1t times cosine omega 2t, and I'll get another term, that is 3 Vp cube cosine square or cosine omega 1t times cosine square omega 2t, right? So again, if I just write the components, what will this create? This is going to create, if I expand this, so this is going to create a component at omega 1, and it is going to create a component at 3 omega 1. So omega 1 surely is going to add up to our fundamental, but the assumption is that it's a weakly nonlinear system. That is, your A3 times VP cube terms are not dominant, so they will probably not at lower amplitude levels, whatever be the lower, we have to define that later on. So at lower amplitude level, we can ignore A3, right? We can ignore A3 VP cube. Similarly, this will also have a term similar, but the other two are going to have something interesting. Let's look at, so maybe let's look at this term, because this is right at the bottom, right? So let's look at this term. So what will that term give me? That will give me 3a VP cube. So this is, I'm looking at this term, right? I'm expanding this term. So I'm going to get 3a VP cube, and I'm going to get cosine omega 1t, and cosine squared means I'll have by 2 here, 1 plus cosine 2 omega 2t, right? So again, this is going to give me one term for omega 1, right? So I'm going to get one term for omega 1, basically, right? This is going to give omega term, one term omega 1, which again, a3a times vp cube by 2, I will assume to be, so let me also write down the assumptions. The assumption is a3, vp cube is much less than a1 vp, right? So this is the assumption, right? So if this is not true to the first place, which means your circuit is so nonlinear, there is no point. I mean, nothing is going to work. You at least want the upfront element to be linear, right? So the basic assumption is that it's weakly nonlinear, which means that all the higher order terms are smaller than the fundamental, right? So because now, I mean, whatever I am getting on top of a1 times vp are all having a3 times something squared, something vp cube times something, which means by default we are assuming that they are negligible. But what about the other one? What about the effect of this? This is going to create a term which is 3a3 vp cube over 2 times cosine omega 1t times cosine omega 2t, which seems to be an interesting term. You can use the classical trigonometric identities. I'm going to get 2 omega 2 minus omega 1t plus cosine 2 omega 2 plus omega 1t, right? Okay, without much discussion, I can say that this will be out of band, because I mean, this is around 3 omega LO, which I am not interested. But what about this guy? This guy is around what? This is 2 omega LO plus delta omega 2 minus omega LO plus delta omega 1, which is at omega LO plus 2 delta omega 2 minus omega delta omega, right? So now after mixing, so after mixing, I just say that this goes here and it mixes with omega LO. So what do you get? You get the terms of 2 omega 2 minus delta omega 1, and after low pass filtering, this is going to come out, right? So what is the strength of this term? The strength of this term is 3 by 4 a3 times v cube. So again, if I plot this, so firstly, like before, let me plot P in versus P out. The fundamental, if I plot like before, we'll have a slope of 1 dB per dB. What about this a 3 by 4 A3 VP cube? In dBm, if I plot, it is going to have 3 dB per dB of slope, right? So it is going to have 3 dB per dB of slope. And like before, if I extrapolate, the extrapolated version is going to meet the extrapolated version of the fundamental. And if I, there is again name to characterize this, and I'm sure you'll be able to guess what the name is. I earlier on was IIP2, this will be IIP3, this will be OIP3. By the way, I skipped one step here. This stone is called third order. This stone at 2 omega 2 minus omega 1 is called third order intermodulation, or IM3. So similarly, like before, when observed at output, it's called OIM3, and input referred OIM3 is called IIM3, which is OIM3 divided by the linear gain. In dB terms is basically YM3 minus the gain, right, when you are expressing in dBm. Okay, fine. So like before, we would like to understand what is the relation between this A1, A3 and YM3. So like before, you have your fundamental is A1 EP, and your OIM3 term is 3 by 4 A3 VP cube, right? So which means that your VP square is 4A1 by A3, which means that VP is equal to under root 4A1 by A3. So this is your IIP3. This is VP in volts. If you have to convert it to dBm, right? So you use appropriate metric, right? So VP square over 50, and then take dB, and then divide by 1 milliwatt, and then take 10 log of that. Whatever you get, you will be your IIP3 in dBm. Okay. So now in practical, just like before when we were doing IIP2, when you will be able to plot these curves, right? And you can figure out whether your circuit is linear or non-linear or whatever by looking at these numbers, right? So by the way, you can obviously find out what is the values of these ratios by directly plotting this IM3 and finding out IIP3. But as a designer, even before you start designing something, right, in order to get to these IIP3 numbers, you have to design something, right? But even before you start designing something, you need to sometimes have an idea about how distorted your circuit can be, or rather, you would like to have an idea of what this A1, A2, A3 terms might be, right? So this is before you start the actual design. So when you have transistors, you tend to characterize the transistors and to understand what is the distortion characteristics. Similarly, maybe you have some building block, you want to characterize the building block. So how do you go about doing it without really plotting these plots, right? So the way it should go about doing it, I mean, it's fairly straightforward, is to understand the fact that what are the genesis of this A1, A2, A3, right? So note that when I wrote that V naught is A naught plus A1 VI plus A2 VI squared plus A3 VI cube. What are these? From where do we get all these terms? Note that in this case, I am saying that VI is an incremental input, not the total input. That is an important aspect. So we are talking that VI is an incremental input, i.e. the amount of deviation around the bias point, right? I mean, this is basic analog 101. So what do I mean by that? So you have a nonlinear function or you have a nonlinear block, you have an input, but I understand that this nonlinear block is biased around some quiescent point, right? Let's say I call this quiescent point VQ or VIQ with respect to the input quiescent point, and I am on top of that, I am applying an input which is Vi. So this output is whatever this A0 plus A1 Vi plus A2 Vi square plus A3 Vi cube and so on. But if I do a Taylor series expansion of VIQ plus Vi around VIQ, what do I get? I get, obviously I get f of VIQ plus I get f dash first derivative of first derivative of f with respect to VIQ times Vi plus second derivative by factorial 2 Vi squared plus third derivative by factorial 3 times VIQ. And naturally, you can easily figure out from here that this is A0, this is A1, this is A2, this is A3. So how to, in order to get these A0, A1, A2, A3, what do you need to do? Obviously, you have to first plot the total IV characteristics or rather the transfer characteristics of f of v, right? So essentially you are plotting f of v, f of vi, where you have vi, you are going to get some plots, right? And maybe you have decided that this is your bias point, quiescent point, this is VIQ, this is VOQ. So you are going to take the first, so basically your A0, right, is VOQ, that is f of, so this is f of VIQ. So A0 is the bias point. What is A1? You take the first derivative, the slope at this point you get A1, you take the second derivative, you get second derivative by factorial 2 is A2, the third derivative by factorial 3 is A3, as right. So sometimes just eyeballing the plots also will give you an idea, right, if it is a good place to bias. For example, if you see that the plot, that the bias point of VOQ versus VI is not changing drastically, right? It's probably a shallow slope, right? I mean, the second derivative is 0, which means you plot what ideally what you want. You want the A1 to be as high as possible and A2 and A3 to be as low as possible. So what is the next step that you would like to do is plot with respect to Vi the first derivative, that is f dash Vi, right? So you might end up getting a plot which is something like this and this. So the way I have drawn the plot, it looks like it is the slope is going to 0 somewhere, right? And then it is again picking up, something like that. So this is essentially your A1, right? This is the A1 plot. And what is A2? A2 is essentially you differentiate A1 again and divide by factorial 2. So from here you can figure out that if I probably bias my transistor around this point, right, the A1 plot is kind of flattish, which means the first derivative of A1 will kind of be closer to 0, much smaller than A1 maybe, right? So maybe that can give you a better idea of uh, an intuitive idea of where to bias in order to reduce the second order distortion. The best thing is you plot out these plots of f dash versus vi. Similarly, just like you have plotted f dash f f dash versus vi, you plot out f double dash, and similarly you plot f triple dash third derivative, and you are going to get a plot. You are going to get a bunch of plots. From their bunch of plots, you figure out where you want to bias in order to maximize the first derivative and minimize the others, right? So I mean, this is another way of going about figuring out where to bias in order to mitigate distortion. But having said that, very zeroth order, this very zeroth order principle that we learned in the last lecture, that is biasing at a maximum overdrive, right? In general, does the trick. If you can bias your transistor to the maximum overdrive, then in general you see that, yeah, the distortion performances are are generally much better than biasing it anywhere else. But having said that, there are other tricks to cancel out certain types of distortion, and we'll look into that in the coming lectures, right? Okay, stop.